Note the simple fluid power system examples use cylinder actuators relatively similar in size. Consider, however, two different size cylinders forming a force multiplication system, one of the principal applications of fluid power that trades distance for force. When force is exerted on the smaller piston, pressure is exerted on the confined fluid. The confined fluid through the passageway exerts pressure on the larger piston, and it extends with a larger force. However, due to the area differential between the cylinders, the volume displaced in the smaller cylinder only extends the larger cylinder a small distance. In a perfectly lossless system, energy input equals energy output. A small force applied over a long distance equates to a large force applied over a short distance. If you want to think of it this way, a force multiplication system is the fluid power equivalent of a step-down gearbox that trades speed for torque. We'll examine Pascal's law and force multiplication systems in greater detail in later lectures. But for the purposes of this lecture, let's quickly define force as a measurable push or pull in units of pounds force or newtons. Pressure, in contrast, is force per unit area, as in pounds force per square inch, often abbreviated PSI, or pascals, where 1 pascal is a newton of force applied over a square meter. Area is ordinarily expressed in units of square inches or square centimeters. The units tell the story quite nicely. Force equals pressure times area. Pound force per square inch times square inch yields pound force. This is Pascal's law. If a comparatively small pressure acts on a large area, force increases. Think about a sailboat on a light wind day. If you want to go somewhere, you need a big sail. In contrast, on one of those nuking days when fish are being blown out of the water, you might need to trim the sails to stay in control or reduce force. Simply by modifying pressure and functional area, one can control the applied force. Going back to our earlier diagram, this implies that the end result of a fluid power system is ordinarily the eventual conversion of fluid power into mechanical power. Actuators are the business end of a fluid power system where this conversion takes place. Linear fluid power actuators are known as cylinders. Cylinders extend and retract with a definable force, speed, and direction as dictated by the fluid power system pressure, flow rate, and valve position. Cylinders are ordinarily represented schematically as one would see them if bestowed X-ray vision and examined in profile. Pending construction variants, the schematic symbol may be modified accordingly. Rotational fluid power actuators are known as hydraulic motors. Motors turn clockwise or counterclockwise with a torque and rotational speed, as dictated by the fluid power system pressure, flow rate, and valve position. You'll note the hydraulic motor schematic symbol is essentially the opposite of a pump. It's an actuator that converts fluid power to rotational mechanical power. Its schematic symbol has arrows pointing into it, meaning it is consuming fluid power and converting it to rotational mechanical power. Note if the hydraulic motor is bidirectional, i.e. you can spin two opposite directions, it'll have two arrows pointing in opposite directions. Again, the arrows indicate that the hydraulic motor is consuming fluid power to our system, whereas the arrows in a pump indicate the pump is providing fluid power to our system. Both these actuators, cylinders and motors, can be used to lift, lower, push, pull, tip, tilt, turn, crush, pound, or otherwise manipulate a load. Keep in mind, mechanical linkages can modify the initiating motion. A linearly actuating hydraulic cylinder can turn or tip a load using a pivoting mount. If you step back a bit, you can think of a fluid power system just like every other system you've ever looked at. There's a power source, a means of transmitting the power, and a load being manipulated. Some of you might be like, wait a minute, hold everything. You mean to tell me that a motor converts electrical power into rotational mechanical power? A pump converts rotational mechanical power into fluid power, The fluid power system controls and measures pressure, flow, and valve position just so some dumb hydraulic motor can convert fluid power back into rotational mechanical power? Why didn't you just use an electric motor in the first place? Can't an electric motor just convert electrical power straight into rotational mechanical power without all the hoo-ha and hand-waving and dirty, greasy, noisy hydraulics? My question exactly. There are advantages and disadvantages to be considered every time energy changes form, and complexity, cost, and efficiency are at the forefront of these considerations. Systems need more complexity, like Portland, Oregon needs another Thai food cart. With each energy transition, losses occur and troubleshooting opportunities magnify. Losses in fluid power systems include, but are not limited to, heat, unintended pressure drops, friction, noise, leaks, and resistance in hoses, piping, and fittings due to kinks, twists, and bends. We'll discuss efficiency in a moment. However, complexity and accounting for inefficiencies can be an acceptable trade-off if one form of power transmission presents notable advantages over others. When it comes to rotational actuators, the electric motor is my weapon of choice. I am not going to build a high-range electric car driven by a hydraulic motor. This being said, an excavator with a fluid power system driven by an internal combustion engine can power rotational actuators and a harvester attachment to cut, limb, and manipulate a huge tree without the necessity of powering an electric motor. I'm equally a huge fan of hydraulic cylinders when it comes to linear actuators. I'm not going to lift a bridge with an electrical solenoid, a comparatively weak linear electrical actuator best suited for small-scale movements with very limited holding ability. This being said, I am going to use an electrical solenoid instead of a huge high-pressure hydraulic cylinder to close a tiny electrical switch in a relay. These examples suggest that there are applications and scales befitting one form of power transmission over the other. Fluid power systems, particularly hydraulic systems, are known for their ability to manipulate or lift large loads and keep them lifted with no additional expenditure of energy. Fluid power systems, in contrast to electrical systems, are also known to have lower initial cost. This does, however, come at a price. Fluid power systems are notoriously noisy, they have cleanliness and environmental concerns, and making up for the lower initial investment cost, require routine maintenance that, if neglected, can lead to systemic failure. The progressive decay of oil exposed to excess heat is a classic example. Additionally, fluid power systems come with unique safety concerns, principally the ever-present possibility of catastrophic ruptures and pinhole leaks associated with high pressures, the slip, trip, and fall hazards presented by spilled hydraulic oil, and the very real possibility of having valuable portions of your anatomy crushed to a pulpy goo between an irresistibly moving hydraulic actuator and an immovable object. Hybrids of different systems exist for the purposes of mitigating disadvantages and maximizing advantages. Consider an electrically controlled hydraulic system where a high-pressure hydraulic cylinder is controlled by a precise and responsive electrical control system. Astounding speed and accuracy can be achieved, all without sacrificing the immense lifting and holding capability of hydraulics. As I like to think of electrically controlled hydraulic systems, hydraulics are the muscle, and electrical control is the brain. Let those forms and methods that excel in one particular function perform that function to the exclusion of all others. Ultimately, regardless of the flavor, the different aspects of a larger system work together toward the fulfillment of a goal. Returning to our previous discussion on fluid power properties, let's briefly discuss how these properties are controlled and measured by a fluid power system to perform a task. Pressure, the property that influences the actuation strength of a fluid power system, is largely governed by pressure control valves. Pressure control valves include, but are not limited to, pressure relief valves, sequence valves, counterbalance valves, pressure reducing valves, and unloading valves. Don't bother differentiating between these very similar looking schematic symbols right now, because we'll revisit each of these pressure control valves in a later lecture. Each pressure control valve performs a specific function that ultimately influences the strength of the fluid power system. Pressure is measured using a pressure gauge or manometer, symbolized by almost a clock-looking dial with a needle that points at the pressure reading. Pressure switches and pressure sensors, sometimes called pressure transducers, perform automatic monitoring of pressure for electrically controlled fluid power systems. We'll examine these measurement devices in greater detail in later lectures. Flow rate, the property that influences the actuation speed of a fluid power actuator, is governed largely by the pump and prime mover combination. If a pump has a certain volumetric displacement per revolution, the prime mover can vary rotational speed up or down to change flow rate. Similarly, if the prime mover remains at a fixed constant speed, a variable displacement pump can vary the displacement per revolution to change resultant flow rate. Flow control valves can then be used to throttle flow rate down from there. Flow control valves ordinarily feature a restricted orifice that can be varied opened or closed as conditions dictate. Flow rate is measured using a flow meter, symbolized by a baseball-looking thing. Flow meters are ordinarily direction and gravity dependent, meaning that flow to be measured must come in the indoor and out the outdoor if the flow meter is to return accurate data. Additionally, some flow meters must be vertically mounted such the flow rate goes upwards through them. A flow meter intended to be mounted vertically, in to out, bottom to top, won't read accurately if it's mounted on its side, upside down, or if the flow is routed through it backwards. A needle slides up and down on a scale, indicating flow rate in the desired unit. Additionally, flow switches and flow sensors also exist to automatically monitor flow rate for electrically controlled fluid power systems. Finally, valve position, the property that influences actuation direction of a fluid power actuator, is governed largely by check valves and directional control valves. Check valves are one-way valves that allow fluid flow in one direction but disallow it in another. The schematic symbol for a check valve looks like a ball in a seat because that's exactly what it is. In the block position, the ball is forced onto the seat and no fluid can flow. In the flow direction, the ball is forced off the seat and fluid can flow. Directional control valves are valves that can be shifted from position to position where pressurized flow, P, is routed to one actuator port, either A or B, and the opposite port is routed to tank, T, or in the case of a pneumatic system, E, for exhaust. The schematic symbol for a directional control valve includes a means of positioning the valve for a deactivated position, ordinarily a spring, a means of actuating the valve, either manually or electrically with a solenoid, a finite number of positions the valve can be placed in, and a number of passageways that can be connected or disconnected based on the position. As a preview of how a directional control valve operates, consider this three-position, spring-centered, manually actuated directional control valve with a closed center, a straight-through position, and a cross-connect position. When the valve is in the spring-centered, closed position, the hydraulic cylinder neither extends nor retracts. Given liquid is an incompressible medium, this position could be used to quasi-indefinitely hold a load in position. If an operator manually shifted the directional control valve to the straight-through position, pressurized flow is routed to the A port, and the B port is dumped to tank. In this application, the cylinder would extend. If an operator manually shifted the directional control valve to the cross-connect position, pressurized flow would be routed to the B port, and the A port is dumped to tank. In this application, the cylinder would retract.